Welcome to the Swine Health Blackbelt Podcast, the latest swine health research digested for you. My name is Clayton Johnson, your host for today's episode, and I am very pleased to be joined by Dr. Nakarin Pamornchainavakul with the University of Minnesota. Dr. Nakarin, welcome to the podcast.
Yeah, nice to meet you, Dr. Johnson. My name is Nakarin Pamornchainavakul. Right now, I'm a Ph.D. candidate at University of Minnesota, College of Veterinary Medicine. I graduated from Thailand with DVM program, and right now I'm pursuing Ph.D. Yep.
Very good. Very, very nice to meet you, and I look forward to talking about your work. As I understand it, it's very important work. You have been researching a very important and unfortunately a very infamous PRRS virus that's been circulating in the industry, the infamous 144 Lineage 1C variant. Dr. Nakarin, what have you been working on with that virus specifically?
Actually, there's a lot of research out there about L1C 144, but on my perspective, we wanted to see the origin of this variant of concern of PRRS in the US, because if we know like where's the origin of this one, and also which variant of PRRS in the past would be like a potential parent for this variant, we may find some like implementation that we can solve this problem. That is the first question for our research.
Very good. I think one of the questions that producers always have when they get PRRS is, how did I get infected? And then take that up one step. When we have a new PRRS virus like this, we say, how did this happen? Where did this virus come from? I think producers generally know that PRRS mutates a lot, but we don't necessarily know the specifics. Could you talk to us a little bit, Dr. Nakarin, about how you investigated the origins of this variant?
So at first, we named this variant based on just only 𝗵5 gene that most of the people in the field use to classify PRRS into 𝗵𝘀𝘁𝗃 typing or lineage or sublineage. But for us, we think that 𝗵5 gene is just 4% of the whole genome sequence, whole genome of the virus. So we want to know like maybe other genes on the virus genome maybe is really important, and it may cause some kinds of variants that we faced like last year from L1C 144 variant. So that's why we just try to sequence the whole genome sequence of the sample represent the outbreak in the field in the Midwest last 2 years, and try to search the potential parents that already existed in the US on GenBank database.
Excellent. So your work worked with whole genome sequences and GenBank to try and understand the ancestry of this new variant virus.
Mm-hmm.
What was the lineage look like? Who are the relatives? Who are the direct ancestors, hopefully? Were you able to find the direct ancestors of this virus or ancestor, where the virus originated from?
Frankly, we couldn't find the direct parent for sure, because we didn't keep sequence every single virus in the field, right? Mm-hmm. But we find some potential parents of this variant. Mm-hmm. At first, that this variant was called L1C 144 because of their 𝗵5 gene. So that part of the genome, like 𝗵5 gene and other genes around that gene, classified as L1C. It's grouped with other kinds of L1C thing. The people in the field may know as 144 virus. But we found that the first part of the genome called NSP2, that highly involved in the replication of the virus, how virus replicate themselves in pig cells, and also expand their population. That one, it has a L1A structure, NSP gene, which it might or might not be the thing that caused the outbreak. We don't really know about that. We have to prove that by experiment. But at the end, we found out that at least this kind of mechanism, evolutionary mechanism, which called recombination, caused this kind of variation. It's just like a swift of the change of the virus. But we don't really know this caused this kind of massive outbreak or not. But yeah, you can see from the field.
Sure. I think most of us are pretty familiar with recombination as it relates to influenza virus.
Mm-hmm.
We've all heard about the triple gene cassette in many of our swine viruses, and the fact that our swine flu viruses often contains pieces of human influenza strains, avian influenza strains, and swine. Is it somewhat similar, this recombination process, with PRRS in pigs, in that if you have multiple strains infecting the same cell in the pig, those strains can recombine in that cell to produce an offspring that contains characteristics of both?
Actually, the concept of recombination and reassortment in influenza is almost the same, but it's a bit complicated in PRRS because for influenza, it is a segmented virus. So the reassortment process just exchange the segment to each other in the same cell for sure. But that one, you pretty sure that, okay, this segment just exchange the whole thing. But for PRRS, it is a linear RNA virus. So we don't really know which part that this kind of PRRS can exchange this part to each other on the same cell. It's really random. So we don't know which position, which part, which gene would be exchanged to each other. That's the problem. So it's really random.
Mm-hmm. It can be random in terms of where within the virus it's received its ancestry. It's not like you're saying a segmented virus where it's, okay, well, this gene segment came from this parent and this other gene segment came from a different parent. Within an open reading frame, you could have parts of both parents present within that open reading frame for PRRS. Is that correct?
Probably, because sometimes, let's say, for open reading frame, sometimes it's not that long enough to recombine. But let's say PRRS virus genome has like major 3 parts. Yeah, within that big parts can be recombined to each other. But for each of, let's say, within just only all 5 genes, it's hard to find a recombination within that. So that's why we can use that gene to classify PRRS into many sublineages without like confounding from recombination. But as a whole genome, it's really hard to define that.
Do you think you would have been able to come to your conclusions and help to understand the ancestry if you would have limited yourself to just 𝗺5 sequences? Or is the whole genome really sequencing essential to this sort of work?
Actually, for my work, for the researcher, we prefer whole genome sequences. But we know that it's right now still expensive, and you have to spend a long time to sequence that, longer time to sequence that. But if you want to just like investigate what happened in your farm using 𝗺5 right now, it's okay to compare your variant with the previous variant like that you face on your farm. But the problem is, what if you got almost the same 𝗺5 gene to the previous time, but the clinical presentation is much different to the past? That's the problem. That's why at that time we may need whole genome sequence to observe, okay, maybe other genes apart from 𝗺5 cause something to in the virus and cause something in the farm. Yeah.
Very good. Thank you. What take-homes would you suggest our audience should be aware of? What are the practical applications of your work and your understanding of the lineage of this new variant 144 Line1C?
Yeah, actually, as you know, PRRS virus is RNA virus, is mutated very fast. But more than that, it's not just the point mutation that they just change the nucleotide on their sequence. This one, recombination, as you know, it can change the features of the virus so fast, and it can create like a lot of variation of PRRS. And this one can create like a new variant, like this kind of L1C144 that may cause a massive losses for your farm. So the key is try not to like keep PRRS virus for too long, especially when you don't really know what is that variant. And after that point, when you just got a new variant without the knowledge also, you may get like a new variant recombined from those two. So try to like avoid PRRS as much as you can.
Yeah, I think
Yeah.
it's a good lesson for us in terms of the appropriate management of PRRS virus,
Yeah.
especially in continuous flow farms like sow farms are. That just choosing to live with a virus has risk beyond just the performance losses of that virus. Because as you demonstrated, if a second virus comes into that farm, you don't just have a potential to deal with those two viruses, but they could recombine to produce a third virus. And that's not only bad for your farm, but that's bad for the entire industry. So I think that's a good practical take home for us as we learn more about how these novel PRRS viruses, these novel strains that tend to decimate our industry every 3 or 4 years, how they get created is, when we hold on to the old strains, eventually when a new strain comes in, we have a chance to create a hybrid that is more robust and better adapted to the pig than its ancestors. And typically that's where we see these big outbreaks that work their way across the whole industry. Thank you very much for sharing that with us. I really appreciate you coming on to the show. And to everybody else, thank you for listening to the Swine Health Blackbelt Podcast. Please check us out at swinehealthblackbelt.com. And don't forget to subscribe to our podcast so that you won't miss out on the next episode. For Dr. Nakarin Pamornchainavakul, I'm Dr. Clayton Johnson. Thank you very much for joining us and have a great week. Hey, everyone. We're always searching for the latest and greatest research to share each week. If you have a swine health-related research trial and would like to come on the show to talk about it with me and share it with our audience, feel free to send an email to healthblackbelt@swineit.com, and we would love to take a look at your research.